Hey there, and welcome to this explainer. Look, if you're deep in study mode, grabbing a quick break between classes, or honestly just trying to understand the physical world a little bit better, go ahead and take a deep breath. Settle in. We are absolutely not doing a high-pressure lecture or some stressful crash course today. Instead, we're going to take a gentle, completely unhurried journey into the hidden materials that shape, well, almost every single aspect of our daily lives. Yep, we're going to demystify polymers and plastics.
Now, before we get bogged down in any definitions, I actually want you to just pause for a second. Look around your room or your desk or wherever you are right now. No pressure to overthink it, just kind of notice what's there. The sleek shell of the laptop you're probably looking at, the protective case on your phone, maybe the lid of your coffee cup, or just the keys on your keyboard. We surround ourselves with these materials literally 24/7, right? But we rarely take a second to appreciate what they actually are at a fundamental level. So what exactly is holding your world together right now?
All right, let's dive into this nice and easy. The core foundation of all these everyday objects is something called a polymer, and our source material beautifully breaks this down into its simple Greek roots. Poly just means many, and mer means units. That's really it. A polymer is basically just a very large macromolecule made by linking a huge number of smaller repeating molecules together. And those smaller units, we call them monomers. It's not some mystical, impenetrable chemical secret you need to stress over. It's literally just many units linking arms and holding hands.
Section 1. The invisible chains.
So to really picture how this works, think of a single paper clip. On its own, it's small, it's distinct, it's just one little piece. But if you start snapping them together, one by one, suddenly you've got this long, flexible, surprisingly strong chain. And that is exactly what is happening inside the plastics you use every single day. Just think about the sheer elegance of this process. And please, do not worry about memorizing the chemical formula here. Just focus on the pattern. You start with these simple, isolated ethylene molecules. Through this cool process called polymerization, they gently link together to form polyethylene. If 100 of these tiny ethylene molecules link up, you get a chain with a degree of polymerization of 100. It's this quiet, invisible chain reaction that takes an invisible gas and magically transforms it into the solid, tangible materials we hold in our hands.
Let's look at another quick example to see how this builds. Consider the creation of polyvinyl chloride. You probably know it as PVC. You've definitely heard of PVC pipes, or maybe seen it in raincoats or electrical wires. And again, just notice that simple repeating pattern. A tiny building block, in this case vinyl chloride, is heated up and kind of coaxed into forming these long chains. And just by swapping out that one starting block, the final chain can be anything from super rigid to totally soft and bendy. It's just a beautifully adaptable system.
Section 2. The engineer's dream and limitations.
Because these molecular chains are so incredibly adaptable, they've completely revolutionized how we build our world. For engineers and designers, plastics are kind of the ultimate cheat code. There's a very good reason they are literally everywhere. The engineering texts point out that they are incredibly lightweight. They have low densities, which makes shipping and moving them super easy and efficient. Plus, they are fantastic insulators. They don't conduct heat or electricity well at all, which, is exactly why they are safely wrapping your laptop charger right now instead of giving you a nasty shock while you study. Oh, and they are highly resistant to corrosion and chemicals. Unlike metals that'll rust or break down when left out in the elements, plastics just hold their ground. They even absorb noise and vibration in heavy machinery. Talk about a versatile toolkit.
But as we all know, nature always demands a balance. The same sources are quick to point out their inherent limitations too. Plastics are combustible, and a lot of them simply cannot handle high temperatures without melting into a puddle or deforming. On top of that, their physical properties can actually be time-dependent. That means they might slowly change or lose their strength over long periods of time if they're constantly under stress. But hey, recognizing these limits isn't really a flaw, right? It's just about understanding the natural boundaries of the materials we're choosing to work with.
Section 3. The two plastic personalities.
So, as we've mastered these polymer chains over the years, we've discovered they basically fall into two distinct behavioral categories. Think of them as two different personalities, based entirely on how they react when things get hot. The big takeaway here is understanding the difference between thermoplastics and thermosetting plastics. Thermoplastics, like PVC or Teflon, are made of these long, linear chains with kind of weak secondary forces between them. What does that mean? Well, when you heat them up, they soften. You can reshape them, cool them back down, and they'll perfectly hold that brand new shape. You can even recycle them from waste. But on the flip side, we have thermosetting plastics like bakelite. These guys are permanent. While they're being made, they form these highly cross-linked 3D networks locked together with strong covalent bonds. Once they are set with heat and pressure, that is it. They are hard and they are permanent. If you try to heat them up again, no way. They won't melt. They'll literally just decompose. So one is incredibly adaptable, and the other is just beautifully stubborn.
Section 4. Growing plastics. The biodegradable shift.
For the longest time, the sheer permanence of plastics was our main obsession. But as our understanding has matured, our goals have totally shifted. We're actually learning to harmonize with nature now, moving away from relying strictly on fossil fuels and petrochemicals, and stepping into this amazing era of material science that literally grows. Enter polylactic acid, or as you probably know it, PLA. This is where the story gets super hopeful. PLA is an aliphatic thermoplastic polyester, but what makes it a real game changer is where it comes from. It isn't pumped out of the ground as thick black petroleum. Instead, it is derived entirely from renewable resources. In the US, it's mostly drawn from cornstarch. In Asia, it comes from tapioca roots, and in other places, sugarcane. We are literally farming the building blocks of our plastics. How cool is that?
Let's just walk through this gentle journey from a farm to a finished product. It starts simply. Renewable crops are harvested from the field. Then, the natural starches inside them are carefully extracted. Next, through the incredibly quiet, totally natural process of bacterial fermentation, those starches are transformed into lactic acid. And finally, through condensation polymerization, those lactic acid units are linked together to become polylactic acid. It takes what usually sounds like this cold, sterile, heavy industrial process and reframes it as an organic, step-by-step cycle of growth.
And this final chemical shift is brilliant. The natural monomer, lactic acid, yields a biodegradable polymer. And because it's quite literally born from nature, it's used in some incredibly diverse, human-friendly ways. We're talking biomedical applications like dissolving stitches and drug delivery devices. It's used for compostable food packaging. And honestly, if you've ever played around with a desktop 3D printer, there is a massive chance the filament you were feeding into it was PLA. It's this super high-tech material, but with a wonderfully down-to-earth origin story.
Section 5. A peaceful takeaway. We've definitely covered some serious ground today, from the basic Greek roots of polymers all the way to farming crops for 3D printer filament. So let's bring it all together and ground these concepts right back in your everyday reality. Look, it's so easy to stare at a textbook or a massive engineering syllabus and just feel completely overwhelmed by all the formulas. But as you've seen today, plastics aren't just abstract concepts designed to stress you out before a big exam. They are dynamic, constantly evolving materials. They are these invisible chains that we are actively learning to improve, stepping away from eternal, permanent waste and moving toward a much deeper harmony with the natural cycles of our planet.
I really want to leave you with this final super reassuring thought straight from the engineering texts about these biodegradable polymers. When they finally reach the end of their life and undergo composting, they yield carbon dioxide, water, naturally occurring inorganic compounds, and biomass. All of that without leaving behind a single trace of toxic residue. By understanding these materials, we aren't just memorizing chemistry. We're literally learning how to build a capable, sustainable, and peaceful future. So the next time you pick up your phone or grab that coffee cup, take a second to appreciate the quiet brilliance of those molecular chains holding your world together. And ask yourself, if we can grow the plastic in our 3D printers from a simple cornfield today, what invisible chains will we learn to grow tomorrow? Thanks so much for hanging out with me for this explainer, and stay curious.